Hello everyone, today I will explain about my reference research paper with the title is Modeling and Validation of BESS using Simple Generic Models for Power System Stability Study. So in this paper, they try to use a new model for BESS. We can see about result of modeling of this new model. So this is for the outline of this paper. They have abstract, introductions, modeling, and detail of modeling, test case, also result and conclusions. So we can discuss about each part in the next slide. Currently, BESS application is increasing in the power system because BESS can providing ancillary service and support to the grid. Also, in the microgrid with the supplement combined both the PV generations, BSS can helpful for the grid. As such, for power system time domain simulations, such as PSSE software, we need to consider about modeling of BSS. In this paper, the new model of BSS is have been developed, which is can be adequately parameterized to represent the dynamic behavior of BSS in power system study. Also, after we model of this kind new BSS, then we compare to detailed three-phase equipment specific model which already used for benchmark in battery study. So in the figure 2 we can see this is the combination of BSS. So example, we have three parts of here in the BSS. The first is REPCA, which means used for the first part, and the second part is REECC, REGCA. So we will discuss about this kind of part in BSS for in the next slide. Also in the figure 5, you can we can see too. This is the benchmark model of BSS. As already explained in the previous slide about BSS component, we can see also in this figure 1 about the full BSS composed of three major components. The first one is battery module, which stores the electrical energy, and the second is the power converter, which is referred as inverters, which convert from the DC current to AC current that inject or absorbed when charging condition from the grid. Also, the last is control, digital control of the BSS that provides the various functionality of the BSS system. Also, the power converter is typically built with the high power insulated, or we know is IGBT, for self-commute switching study, and this kind of inverter can fully capable of full power quadrant operations. Also, in the digital controls of BSS is capable of a suite of functionality including far control, frequency control, fast frequency response, also controlling the rate of power recovery post-fault, and etc. This section will discuss about modeling BSS. So recently, VECC extended to modeling battery energy storage system using the another module. So the key component of this kind of model, we have two parts in here. First is REECC and REPCA, which this kind of model can control voltage, also control frequency. For the detail, BESS can be modeled for the three components like I already said in the previous slide. First is REGCA as the generator converter model. REEC it means electrical controls models, and the REPCA it means energy plant controller version A, which can control the voltage also. Uh, we use this voltage control loop in the RECC model for the appropriately model the voltage control functionality. Also, the active power control arm of the REPCM model, also shown in the figure 4, to emulate the primary frequency control functionality. So in the RECC model, this kind of part will control the voltage, and figure 4, this kind of part in the red rectangle will discuss about the primary frequency control. These sections we will discuss about the detailed three-phase base model, which is also using for the benchmark study of modeling BSS. So this three-phase base model is used and developed from the Northern Power System using the MATLAB simulating software. So the system is designed to for the vendor for the how to specifically for the flow battery study. Also in the figure 5 we can see about the high level block diagram which modeling of PLL, reference frame manipulation for control, details of inverter controls, also the current regulator. But the battery is not model explicitly modeling in this figure 5. Also for the switching study is not explicitly model, but in this control model in the figure 5 is shown for the IGBT modeling. Also maybe some of students not familiar with the PLL, so I put the definition of PLL in this slide, which is we can see in the black rectangle, which PLL is the control system that generates an output signal which phase is related to the phase and input signal, which is we can imagine it's like the feedback controller of or of the common controller in the system. In this section, we will discuss about the test case and simulations. To perform the benchmarking of the stability genetics models, a simple test case was set up using both modeling platforms. So, for the three-phase models, we using the MATLAB simulating software, and for the genetic stability models using the GEPS LFTM software. For the test case is shown in figure 6, which consists of 3 bus, 1 transformer, and 1 BESS inverter, and 1 infinite bus ideal source. So we use this simple test system for simulations. During simulation, we need to check the channel output too. So as shown as in the black rectangle area, we have three part of channel output. The first part of channel output is all three phase voltage and current at the inverter terminals. Also the second is calculated the three phase of power and reactive power at the inverter terminals plus one. Also the last is current real and reactive of commands by the controls. So we need to consider about this channel when simulations occur in the test system. Also for the scenario we have four scenario. First scenario is 16 volts at bus 2. Maybe we need the reason author need to consider about this 16 volt at bus 2 because this simulation help to test and verify the fault right through and voltage current characteristic of the BESS response for severe to moderate voltage dips. Also, the second scenario is several key reference, V reference, and P reference step tests. These tests help to verify the dynamic response of the reactive power control, active power, and the voltage control loops. And the last and the third is several frequency reference step tests, which this test is help to verify the drop and primary frequency control loops of the BSS. Also the last is some unbalanced faults is simulated too because the author need to observe the behavior of the positive sequence stability models in relation to the actual expected three-phase equipment behavior. So this is the section of the result of simulation. So the author make the comparison between three-phase model and GE model. So for the first scenario is the 16-volt cases. So we can see the result for the first scenario in the figure 7 and figure 8. The reason why the author just make the one of the 16 because the 16-volt case is similar. So that's reason author just make the one of a figure of these 16-volt cases. The only observable difference between three-phase model and GE model is when the fault happen and when the fault clearing time. The reason because the integration time of two software is different. That's reason we have a slightly difference or a bit difference during this period. So for the figure 9, 10, 11, we this is the result of the second scenario, which is the step change and reactive power reference, also step change in voltage reference, and the last is step change in active power reference. So this is the comparison of this kind of step change. So we can see in the figure 9 step change in reactive power reference because the author make a different parameter at 1 second in reactive power. We can see this is the result of the voltage output when the author make the higher value at the 1 second in reactive power, the voltage is increased too. So it's also same with the another parameter. It's same with the voltage. When the voltage is rise up, the value of reactive power is higher too. But when the active power is going down, we can see the voltage is going down too. But maybe the comparison between three-phase model and G model, we can see here the reason a little bit a difference between two models, because in the REGCA model, or we can call the generator model, there is a difference value of the time constant. That reasons there is a little bit difference between between two model and in the two software conditions. In this section, we will discuss about the third, fourth, and fifth scenario. As shown as in the figure 12, it means the simulation of injecting step frequency reference on the primary frequency response. Also in the controller between three-phase model and GE model. So we can see in the EPCA model, which it is the generic model, GE model, we can see the author put the frequency reference. Also in the three-phase model, the author put the value of F comment in this model, and then this is the result of this comparison in the 1 second. So we can see there is a higher of power the increasing of active power at 1 second time, but there is no difference. There is no difference between reactive power and voltage value. So maybe we need to consider about this kind of part. So figure 12 is an interesting simulation. In this case, a step was injected, frequency reference of the controls F command in figure 5, as already said before, F command, and the frequency reference in the frequency reference in the REPCA model. This is the part of frequency reference. This simulation is exercise the primary frequency response control of the BSS. Again, we can see a very good correspondence between three-phase model and GE models. This spike in three-phase models around 0.85 seconds is an artifice of three-phase model. Actually, this is the original, or there is the author don't make a difference parameter, but this is the happening in the three-phase model. Also in figure 13 and figure 14, this is the unbalanced fault cases. This is a very interesting result too, because it can be seen in that case the active and reactive current produced by the controls in response to the single line ground fault almost identical for both three-phase model and the GE model. So we can see, but maybe there is a little bit difference between in reactive power response. So yeah, just this a problem for the reactive power value. So almost of them is almost same. So this is the last of this paper conclusions. So the results here so that one can quite successfully model the performance of BESS system. So based on this paper, we can use this kind of model for BESS study. Uh, there are, however, still some minor discrepancy, but which are all explicable, but we don't need to worry because the author say is explicable. It means there is some explanation between difference of three-phase model and positive sequence modeling. Finally, since generic models have been implemented in GE, also Siemens PSSE, PowerWord Simulator, and PowerTech Lab, another software, we can use this kind of BESS for dynamic behavior of renewable energy system to put in the this kind of software for the power system study. So that's all for the paper and the conclusions. So thank you. So in this part I will explain about the simulation progress of my reference research paper, but unfortunately my PSAC software is not supported because RECC1 or electrical control model of for utility scale battery energy storage is just used for the this version, at least 33.12 or 34 versions, but my best easy software is not supported, so I cannot use this kind of part. Some of I search in the another reference, they say we can use REC AU1, but in REE in another parameter like this electrical control model, they don't have the SOC. I mean, if we don't have SOC, it's not battery. That's reason I cannot use the latest model before this. So maybe if you want to use BESS, first of all you need to check this model is available is your PSSE or not. If this model is not available, I recommend you to upgrade PSSE software or make another modeling BSS like CBase that already explained with Miss Dwi in the previous meeting. So that's important. We need when you make a new modeling of BSS, first of all you need to check if this is available or not in your software. So this is the latest of my presentation file. Because I don't have RECC1 in my PSSC software, that's reason I try to change and make a new BSS model based on CBase. So recently I make a new I try to make a research on control algorithm purpose method on the CBase. So I tried uh, recently I tried to use a combination of two paper for the main reference. First is from the Miss Dwi paper, and the second is from Professor paper. So I try to make a control algorithm to simulate in network system. So recently I tried to make a simulation based two conditions. Maybe in the mystery paper already explained about how to control p-base based on event based and frequency response operation. So maybe I try just a little bit changing. In the event base I try to make a RAM rate setting and then maximum capacity. So the difference is first when the uh, frequency disturbance, the battery will be have a RAM rate, first RAM rate condition, and then goes to maximum capacity. So that's reason the frequency stable is more higher. But in the professor paper uh, discuss about additive truth, non-additive truth, and anything value put in this study. So I just try the one of purpose method of professor paper using the non-adaptive. Maybe it's already explained to in the uh, autumn conference with my friends is Park Junsu, which already proposed to in this using same method for the non-adaptive proof. So this is the result of non-adaptive proof. So maybe maybe for the next simulation I try to another research control algorithm purpose method. So that's all for the situation of my research. Thank you for your attention. Have a nice day.